The significance of the dot product comes to us from the geometric interpretation of what the dot product actually is. So geometric interpretation of two vectors is that these are directed line segments. We'll call this one u, and we'll call this one vector v. Now, one thing that the dot product is going to be great at measuring is what is the angle that exists in between two vectors. That is the acute or obtuse angle rather than the larger angle that we see on the outside of this. Now, this angle needs a name. Let's call it theta for the time being. Now, what we're going to do is we're going to connect these two guys together right here, the terminal points. Now, the geometric interpretation of this is depending on which way I orient the vector. This could be either u minus v or it could be v minus u. For example, if I were to orient it in this fashion, where the initial point is over here and the terminal point is over here, that vector would be u minus v. Because then if I add together v plus u minus v, I would get u. However, what I'm going to do is interpret this geometrically as though it is a triangle rather than in terms of vectors. So, that's not a great interpretation of what I just did, but that's okay. This triangle would have sides of the magnitude of u, the magnitude of v, and the magnitude of u minus v. Now, when you have the three sides of a triangle and you're trying to figure out information about one of the angles, these can be connected together using the law of cosines. The law of cosines states the following. Take the side opposite the angle, so magnitude of u minus v, quantity squared, is equal to the sum of the squares of the other two sides, so magnitude of u squared plus magnitude of v squared minus 2 times the magnitude of u times the magnitude of v times the cosine of the angle in between them. In the event that you're dealing with a right triangle, then theta would wind up being 90 degrees, and this would be 0, and this term would go away, and you would have nothing but the Pythagorean theorem left over. Now, assuming that we know the components of the vectors, this is going to get very big very quickly, so buckle up. This one's going to be good. So, to take the magnitude of something, we're supposed to take the sum of the squares of the components and add them all together and then take a square root. This square is going to cancel out that square root. So this will be u1 minus v1, quantity squared, plus u2 minus v2, quantity squared, plus u3 minus v3, quantity squared. This is going to be equal to. I'm going to do the same thing for these two right here. That'll be u1 squared plus u2 squared plus u3 squared, plus do the same thing for the magnitude of v squared. That'll be v1 squared plus v2 squared plus v3 squared. The rest of this I'm going to leave in its current form, assuming I can even fit it on the page at this point. Gonna make it work. Gonna make it work. Holy crap, I made it work. All right. What's not going to work is this next line, because this next line is going to be a lot of algebra. I'm going to expand this whole thing over here. So I'm not even going to try to make it fit on one line. This is going to be two lines. So this will be u1 squared minus 2 u1 v1 plus v1 squared. Do the same thing for the second one. Expand that. u2 squared minus 2 u2 v2 plus v2 squared. Plus, expanding this one, u3 squared minus 2 u3 v3 plus v3 quantity squared. And this is going to be equal to what we still have on the right hand side. This is u1 squared plus u2 squared plus u3 squared plus v1 squared plus v2 squared plus v3 squared minus 2 magnitude of u times the magnitude of v times the cosine of the angle in between them. Now the good news is we are going to be able to cancel out a lot of things at this stage because there are a lot of quantities that appear on both sides of the equation that we can start subtracting. For example, I can subtract a u1 squared from both sides. I can subtract a u2 squared from both sides. and I can subtract a u3 squared from both sides. I can also subtract a v1 squared from both sides. I can subtract a v2 squared from both sides, and I can subtract a v3 squared from both sides. You'll notice that everything left on the left-hand side has a coefficient of -2, and everything left on the right-hand side has a coefficient of -2 as well. So for my next step, I'm going to divide both sides by -2. We're going to wind up with the following. u1 times v1 plus u2 times v2 plus u3 times v3 is equal to the magnitude of u times the magnitude of v times the cosine of the angle in between them. You'll notice that what we have left on the left-hand side is exactly the definition of our dot product. So not only is this the significance of the dot product, this is also a theorem. In order to calculate the angle between two vectors, you'll need to take their dot product and find both of their magnitudes. Through a little bit of algebraic work, assuming that neither of these guys is equal to 0, we can derive the following. The cosine of the angle between the vectors is equal to the dot product of u and v divided by the magnitude of u times the magnitude of v. Now the other thing to point out here is that if I take u divided by the magnitude of u and v divided by the magnitude of v, what we get are unit vectors in the direction of u and v. And if we go back to the beginning of all of this, the lengths of the vectors should have no impact on the angle in between them. U can be as long as it wants to be, v can be as long as it wants to be. It shouldn't have an impact on the angle in between them. There are some implications that come out of this. Some of the implications are that if the dot product of two vectors is equal to 0, the vectors meet at a 90-degree angle. However, as soon as we get up to 3 dimensions, we use a slightly different name for perpendicular. They are orthogonal to one another. Orthogonal is basically just the higher dimension definition of perpendicular. So in a plane they'd be perpendicular, but in space they are orthogonal. The other thing that this lets us know is that if one of the vectors is the 0 vector, then the vectors are automatically orthogonal. If we take the dot product of the 0 vector with any other vector, we're guaranteed to get 0. So that's what we call the trivial part, I guess. Additionally, once we actually calculate this thing, taking an arc cosine will let us know what the angle is. Other implications: if u dotted with v is greater than 0, theta is acute. If u dot v is less than 0, then theta is obtuse. Simply because when we take the inverse cosine of something positive, since these magnitudes are guaranteed to be positive, we're guaranteed a quadrant 1 angle from the unit circle, so that'd be something that's between 0 and 90 degrees. Whereas if we take the arc cosine of something negative, that guarantees a quadrant 2 angle, which would be an obtuse angle between 90 degrees and 180 degrees. We'll do some examples in the next video.